And to start, let's talk about composite material. When we look at the composite material as a bulk material, it is macroscopically homogeneous. We do not see any irregularities there. But as soon as we zoom in, we can see that a composite consists of a continuous phase and some additives present here. They can be particles or fibers or something else. The continuous phase makes the matrix or the binder of the composite. And the inclusions, they are called reinforcement or charge. And what is remarkable about composites that both matrix and charge introduce particular material properties to the composite. When they are separate, the material properties can be different. But when they are united, the composite itself gets something superior. So both matrix introduces stiffness or flexibility, and the charge or the reinforcement introduces higher strength and better material properties. What are the advantages of the composites? I guess they are well known, but I will talk about them once again. So they are lighter, but they possess high mechanical stress. They can perform at elevated temperatures. They are heat resistant. They can possess flame retardant properties, superior thermal properties due to the properties of the charge. They are tougher, so they require less maintenance. They can be chemically resistant, but they possess plasticity, so we can design a particular form out of composite material and have no problems with process. Having all of this in sight, we of course aim at production of the composite materials. And when we are designing a composite, we are starting with the molecular structure of it, molecular properties, which will determine in essence the material properties of the composite. So the molecular properties are divided by those introduced by the matrix and charge, and by the interfacial interactions that occur between the matrix and the charge. And I will talk a little bit more about the interface as it is very important in terms of a composite. So you can see here that the bulk material, this is our polymer. Here in the middle, this is the charge, the carbon fiber that we will talk about. The boundary between them makes the interface, and we can treat the charge in such a way that it will make an interface that will also ensure a better connection between the matrix and the charge. Talking about how we can ensure that the charge is better connected to the matrix, that can be via mechanical bonding. So there are some irregularities on the surface that interpenetrate to each other. Electrostatic bonding. If there is a phase charge separation between matrix and charge, chemical bonding, we can induce some chemical interactions between matrix and charge and also enhance the bonding, and interdiffusional bonding, when the molecules of the matrix and charge interpenetrate each other and in that way ensure better interfacial bonding. So once again, interfacial interaction will play an important role in the material properties. That's why we're paying so much attention in them. For a given system, more than one mechanism can occur. And during the processing, we can influence the bonding in such a way that it changes, becomes better, or sometimes worse. That also happens. But in any case, we are aiming at better interaction between the matrix and the charge. What can we do to enhance the interfacial bonding? We can ensure the good contact, so the matrix and the charge interact in such a way that they have a good wetting properties. We can change the surface roughness, and we can treat the charge in such a way that it will interact better with the matrix, as you can see here in the cartoon example, where the charge is treated in such a way that it interacts with the matrix in a chemical manner. Now I will focus on the carbon nanotubes and fibers for polymer composites. So carbon nanotubes are fascinating. These materials, no one could even imagine that they will have such an amazing material properties. They allow us to vary significantly the material properties of the composite due to the variation of their structure. So carbon nanotubes can be single walls or multi-walls. They can possess chirality, their diameter can be different, their curvature will be different, and of course all of that will affect how our composite material performs. The interfacial area of the surface area of the carbon nanotubes is large, so it ensures a good interaction with the matrix. That's why carbon nanotubes can introduce higher composite stiffness and strength. And also, carbon nanotubes can introduce the flexibility to our material due to their ability to deform prior to breaking. So we will explore all these positive material properties to make our composites better. But there are also some difficulties that we need to keep in mind when designing a material. First of all, carbon nanotubes tend to form aggregates. So to make an efficient composite, to make a composite with superior properties, we need to ensure a good dispersion of the carbon nanomaterials in the polymer matrix. During processing, we can destroy carbon nanotubes, and of course that will also decrease the material properties of our composite material. And as I mentioned before, the structural variation of carbon nanotubes is significant, so we need to keep in mind what we are putting inside. If we are changing the source of the carbon nanotubes, that may affect their structure and in the end the material properties of our composite. So carbon nanotubes should be free of metallic and amorphous carbon impurities, and that's, at that manner they are of high quality, which is beneficial for the composite. We can enhance interfacial adhesion by chemical treatment or plasma treatment, for example. So we need to ensure optimal dispersion. And in some cases, we would like to get an aligned distribution of the carbon nanotubes. So some examples when carbon nanotubes can enhance or deteriorate the properties of the material. Here you see an example from literature where the researchers prepared a composite of polystyrene and multiple nanotubes. And you can see that the tensile stress for the composite is actually worse than for the pure polystyrene, meaning that there is not enough interaction between the carbon nanomaterial and the polymer material, and it actually causes disruption of the structure. But with a certain degree of engineering, we can solve this and actually treat the surface of the carbon nanotubes with butyllithium here and make the composite better. Here you can see that the stress strain curves for pure polystyrene are located lower than the ones for with the treated carbon nanotubes. So indeed, we need to keep in mind a lot of points when we are designing a composite material, because we can make actually the material worse. That's the complexity that arises from both the nature of the composite materials and the nature of carbon nanotubes. Considering aggregates, here you can see again a literature example of the carbon nanotubes, multi-wall carbon nanotubes that tend to make aggregates in the polymer matrix. And of course, this will also negatively affect the properties of our final material. So, how can we ensure the optimal dispersion of carbon nanotubes in the polymer matrix? Via mechanical methods, how we process our composite, or via treating the surface of the carbon nanotubes. Either they form non-covalent interaction with the polymer matrix, or we introduce some functional groups that will interact with the matrix covalently.
There is some noise.
The table gives some overview of the methods how to disperse carbon nanomaterials in the polymer matrix. And I will focus here on giving an example, given a research example in a case study. Considering orientation. So as we are talking about fibers, fibers can be randomly orientated or aligned or making a network, and that will also change the properties. For example, we can expect that parallel orientation, aligned orientation of the carbon nanotubes enhance the mechanical properties, but random orientation will affect thermoconductive properties, for example. And now let me give you the case study, the example of short carbon fiber reinforced composites that we processed via 3D printing. So additive manufacturing is the emerging technique which already finds industrial application in which we print the material, in which melt the material and print it layer by layer. In that manner, we of course decrease the production rate, but we can make a very complex shape. We can use less material, so less waste. We can ensure high quality of a complex structure, which is simply cannot be produced by injection molding, for example. And in that way, we spend less time and effort for the assembly of the complex material. For the composite material, yeah, there are some examples of processing via additive manufacturing techniques, but they are they are rare. So that's why we are making a research in that area in particular. And for the printing technique, I will introduce a fused filament fabrication. This is actually industrially employed technique in which we take a filament, so a wire of a polymer or a composite. We mount it once again in the nozzle of the FFF machine, and then the printing head moves in different direction and prints our shape. So these machines are commercially available, but the main drawback here that we need to produce the filament first, this wire, which is the feedstock for our printer. So our material will be melted twice. First during production of the filament, and second during the actual printing process, which of course can induce the degradation of the fiber or degradation of the polymer matrix, affecting negatively on our material properties. That's why in-house we developed a direct pellet-based extrusion additive manufacturing technique. Here we basically skip the step of filament production, and we take the pellets and the charge. If we are talking about a composite, we mix them in a single screw extruder, which is connected to a nozzle, and then this construction actually works as a 3D printer. So we have a moving platform that moves under the nozzle and prints our part. In this way, we use one melting cycle, so we ensure less degradation of the material. And we are trying to select the settings for the direct pellet extrusion-based additive manufacturing in such a way that the printed parts possess similar properties as the industrially used fused filament fabrication. How can we do that? Let's see the example. So we studied two types of composites. One is with polycarbonate and ABS plastic with a small content of short carbon fibers, and the second is with polypropylene and high content of the short carbon fibers. And first of all, what we tried to do, we used very similar settings for both 3D printers, for the industrial one and in-house developed, and printed tensile bars and impact bars. And here you can see visually that for the FFF printed materials, the surface is smoother. So the printing settings are more optimal in there. Here we can see some small inaccuracies in the printing. We actually can quantify that by optical microscopy and estimate the surface roughness. And you can see that for the FFF printed samples, the difference in the heights of the layers is way smaller than for the pellet-based additive manufacturing. So it's kind of the indication that we are not using the optimal settings for the printing. But what about the material properties? We tested the tensile stress, the flexural stress, and actually in both cases the results are comparable. So we can see a very small difference in the tensile properties, while in the flexural properties the difference is larger but still not orders of magnitude. So we consider that here the material properties are quite acceptable despite the roughness of the surface. But then we tested the impact stress and we noticed that it is significantly lower for the pellet-based additive manufactured parts than for the FFF manufactured parts. So this is of course a problem which we would like to look into and which we would like to solve. The same is true for the materials with the high content of the carbon fibers. But here you see that even for the impact stress, the results are very much comparable. So we consider that for this technique, for this particular material, the settings were more optimal. Of course, it depends a lot on the matrix. There we use two polymers, here it is one polymer, but here the carbon fiber content is higher, so we expected that that can cause also problems. So yes, here both techniques show very similar trends. We wanted to explore more the reasons why our pellet-based additive manufactured parts fail in the impact tests. That's why we recorded an optical microscopic images, and we saw voids in the structure. So you can see that there is not an optimal adhesion between the layers. We are printing actually too fast to make the good adhesion between the polymer layers. That, of course, affects negatively on our flexural properties. more insights into the molecular properties, scanning electron microscopy. And here we are trying to see if there are aggregates of carbon fibers when processing the composites via both techniques. And we can see that no matter which technique we use, FFF or pellet-based printing, no aggregates are formed. So we introduce enough mechanical energy to ensure a good dispersion of carbon fibers. We can actually quantify. We are scanning electron microscopy if our processing technique damages the carbon fiber. And here we can see that for FFF printed composites, we get shorter fibers than the ones for the pellet-based manufacture, meaning that indeed two processing cycles affect induce the degradation of the carbon fiber, so it actually breaks. So this technique is potentially bad, considering the preservation of carbon fiber. So what we can do to enhance the properties, keeping in mind that actually the polymer matrix fails. So during the printing, we print layer by layer, and there is a void when the layers are not optimally interacting each other. We can actually anneal our material, so heat it again and let it reduce the mechanical stress inside and close those voids. So in that way, we will ensure that we have less voids. Or we can treat with plasma the carbon fibers and enhance the interaction between the fiber and the matrix. So actually we did both of that. Here you can see the results of the annealing. And indeed, we saw that the modulus went up and the flexural strength went up for the treated and non-treated materials. So indeed, annealing is a good way to enhance the material properties of such processed composite. Next, we also tried the plasma treatment, but the results were not that significant. In one case, we observed better flexural properties, but they are all comparable. So this part of the research is still ongoing. So let me summarize what we've been talking about today. I gave an introduction about the composite materials when the mixture gets enhanced properties. I highlighted the important points to keep in mind when designing a new composite material, molecular properties of the matrix and charge, even distribution, and probably in sometimes orientation. And I gave a case study about the 3D printing of short carbon fibers composite and polymer matrix. Thank you very much for your attention.
So, yes, I will use your microphone to make it easy not to switch always. So,
sure.
Mariya, a lot of thanks for presentation. To give, let's say, in a nutshell, part of research which is going on also in our research group in our department. So, in between, yeah, you saw me busy trying to solve together with Nicolina the access of everybody. So I'm happy that almost everybody now shared also online. For this afternoon, we will find also solutions for the breakout rooms, so to see how to solve the problem. So we now have a break. When I know the program by mind, we now have a break up to 11:30. So the one who are online, don't move, let's say, the chat. We will come back at 11:30 for the STSM presentations part 1, which will be presentations from Muslim Kaplan, Frank Clemens, and Jelena Lubura. I hope I pronounced well. So let's now take a break and start again at 11:30.